In this video, we'll begin our discussion of section 7.3. This will be properties of the Laplace transformation. In this first video, we're going to work on what is called the first translation theorem. Let's talk about what a translation is. You guys have seen translations before. You may have not saved it or memorized it into your memory as a translation, but remember if I had the function f of x equals x squared, remember that was our parabola, right? Just something like that. Doesn't need to be perfect here. And I plug x minus 3 in. Well, that becomes x minus 3 squared. Well, that was just the parabola above shifted to the right 3, right? And that was what that was. It was a translation to the right. All right, that's what we are really talking about here in this theorem. So take a look at this theorem. We're going to prove it so you can see why it works. It says, okay, that's Laplace transformation of f of t be big F of s, and a is any real number. So they're saying the Laplace of e to the at of f of t, and they're saying this is just a translation on the s-axis. Right, this would have been a translation on the x-axis, moving it right 3 up here. Well, this just moves it right A, or if A was negative, it'll be left A. All right. How we write this notation, it's going to look like this, and this isn't going to make a lot of sense right now, what that is, and it'll make more sense once we do an example down below. I'll show you how that works. Okay. Let's go ahead and prove this idea just mathematically, and then maybe we could talk more about this last equality here and what it means. Okay, so we're going to prove this, just a real sloppy proof, nothing real formal. So we'll just say Laplace of e to the at f of t, and this is going to equal, okay, this is just the definition, 0 to infinity of e to the negative st, e to the at, f of t, dt. Okay, so we're going to combine our e's here. We're trying to get to the normal definition of just little f here, but maybe instead of having a negative st, we'll have a negative, and we're going to put s minus a or something like that in here. So we can make that happen by manipulating the stuff around. Notice they both have a t, and then so I'm going to do a negative, and I'm going to have an s minus a t. So notice that is the Laplace, like how it would be if I were just to put, instead of this s minus a, I would put an s. So it's a like plugging in s minus a instead there, and then everything behind looks like the rest of the Laplace. So this is just capital F of s minus a. So what this means, and let's see if I can make sense out of it here to you, and if not, I think you'll get it with this next example. This is just take the Laplace of what the normal function was. Right? So we would treat it like normal, like there was no s minus a or anything. It was just normal t. There was no e to the at at the beginning. Just take the normal Laplace of that function. And then once you do that and you have your answer, you're going to take s and you're going to change it to s minus a. It's like a U sub in a way, I guess. You could think about it that way. We just don't error to get du because we're working in terms of t, and we're just subbing an s and an a. So you could think about it, I guess, that way and returning the u later. But that's the notation for that. So let's try an example here. So the Laplace of e to the 7t, t to the fourth. I'm not going to run it through all this stuff up here. We're just going to try the theorem. Okay, the theorem says you just do the Laplace of the function, which was just t to the fourth, and then once we have our answer, make sure we take our s's and change them to s minus 7. A in this case was 7. All right, so I keep going. Let's go to the right because I don't think we'll have space to go down. Laplace of t to the fourth is going to be 4 factorial over s to the fifth, remember n plus 1. And then I still have this here because I've got to remember to do it. And then our final answer here will be 4 factorial over, and we're going to plug in s minus 7 where the s was. So s minus 7 to the 5th. There we go. So it's a little quick way to do kind of a sub. We could plug this in into the definition and work it out. I think we've done some of those, but this is much quicker using that theorem. All right, let's do the second definition example they have here. I mean, so e to the negative 4t cosine 5t. Okay, so I see the e on it, and this new translation theorem says if I have e times a function, I can use this theorem. So this is going to be the Laplace of cosine 5t. And then once I get an answer to that, I'm going to change my s to s plus 4. And that's because this was a negative. Look up here, it was 7. We used a minus 7. It's the same thing. Okay. So Laplace of cosine. Remember, I have an s on top. And then I'm an s squared plus k squared. In this case, 5 was k. So we have that. Don't forget to leave this on here. That's going to be probably the big mistake, I think, with it was for me. Is I would get my Laplace here, and then I'm like, oh, yay, I have an answer, but you have to fix it. So I'm going to have an s plus 4 on top, and then an s plus 4 squared plus 25. There we go. The theorem is extremely helpful. I hope you understand why it works with the way we proved it up there. So what is happening is once we put in, if we multiply a function by this e to the at thing, it's actually going to result in an answer that shifts our original answer that same way, right? Where this is that s minus a here, right? It shifts it. So the e is like for Laplace, and e is how we can move the algebraic equation on the other side. In s, we can move it left and right. Okay. This is mainly going to help us go forward and backward when I change the equation on the right side of our diffie-q. All right, we have a couple more going backwards. So this is going to take some construction to get there. Okay, so let's take the first thing. I'm not going to write it, the inverse Laplace to break this apart. So I'm just going to think about it like this. All right, we're going to use partial fraction decomposition here, not partial fraction decomposition. Okay, and we're going to get a over s minus 2 plus, and then we have a repeating here, so we just repeat it. And since we just repeated it, we get to use another constant. All right, if I multiply each side by the s minus 2 squared, I'm going to get 5s equals a times s minus 2 plus b. Nice pretty equation here. All right, so we'll do s equals 2 first. Just doing our fraction decomposition, so we'll get 10 equals b. And then if we do s equals, I'm going to do a 3 here. I get 15 equals a plus 10, which tells me that a is 5. Okay, so I'm going to rewrite, we're doing that top one still, or the left one. So I'm going to rewrite it to 5 over s minus 2, and then plus 10 over s minus 2 squared. All right, we can rewrite this. I'm going to go ahead and break these up, and this could be, there's a way to think about this that you guys have seen already. You should be able to see that that's that e function, but we're going to use this theorem. So this is actually the inverse of 5 over s, but I have to keep in mind, and we put this on the inside of it, that I need to change the s to s minus 2. That's going to help me remember to do the e. And then plus the inverse Laplace of 10 over s squared. And then I need to remember to take my s to my s minus 2. All right. So we take our inverse Laplace of 5 over s. All right, remember that's just a constant. And then normally I would change the t to the t e to the 2t, right? Or I'd put that in there. We need to still do that. So we'd have 2t here. So you just take whatever the Laplace of this is, and then this is going to that second thing. Sorry about that. This second thing here is going to result in e to the 2t. This thing here is going to result into an e to the 2t. Maybe write yourself a note there, knowing that that's going to happen. And then that second function is going to be 10. And then we need to manipulate that one a little bit. So let's actually write it out like this. I'm going to do 10 times. And I have found that if I just pull all the constants out, students have an easier time thinking about it. So that's why I'm writing it out like this. If you can manipulate your 10 and go from there, kudos, do it. If not, here's a way to think about it. I just pulled the 10 out. Oh, we really don't need to manipulate this. I'm here, I'm going to write it. This was that square here would be a 1 plus 1. So this would need to be a 1 factorial. 1 factorial, 1 factorial. That doesn't change anything. I don't know why I thought I saw it, but here we go. We'll just go ahead and write it from there. This is 5e to the 2t plus 10. Some of you guys are rolling your eyes really hard at me. That's okay. 5, 10t, and then e to the 2t. There we go. So at least we got some practice actually on how to do this thing to match it there. Okay, so that's what we have. You could always check it by taking the Laplace and making sure it works out. All right, so now we're going to do that second problem. I know, okay, so let's take our 1 over, and it was s squared plus 4s plus 5. All right. If you were to start trying to factor that, you'd quickly learn that it does not factor. When this happens, what you're going to want to do is complete the square. Now, I'm going to show you a way I've thought about completing the square the way I teach it in my algebra courses now. What you're going to do is focus on just this part for a moment. I draw a little box here, so a square. And I use kind of some like geometric algebra to figure it out. The reason I do this is because I don't have to memorize anything. I can just look at it and figure it out. This goes s squared. And then I have 4 s's to make a square, so I need to put 2s and 2s. So I used up everything I've underlined. Outside of the box, like factors, meaning this is s times s gets me the s squared inside. S times 25 gets me, not 25, 2. 2 times outside, my 2's and my s's and 5's look similar. My apologies for that. 2s, and then this has to also be 2, meaning the box that I complete here needs to be a 4. So if I put a 4 there with s squared plus 4s, and I put a 4, I can actually factor it to s plus 2s plus 2. I'm going to write this out long ways just for a moment. So I get s squared plus 4s plus 4, and then you can manipulate this 5. Okay, I just need plus 1. And notice I didn't change anything. But now what I'm going to do is take this, and we can factor it to s plus 2 squared plus 1, and then a 1 on top. All right. So notice though, we have this s plus 2. So I'm going to go ahead and rewrite this. We have Laplace, and it was inverse Laplace of, and I'm going to write what's there. Notice if the thing that was being squared, if I were to change that, I could have my sign inverse, right? If I had an s squared there, I'd have my sine t inverse. But if the s plus 2 is kind of messing it up, so I'm going to rewrite this as L inverse, and then I'm going to do 1 over s squared plus 1, and then we put this little thing here as a reminder. S was going to s plus 2 inverse, and then remember this is a something telling us that we're going to put an e to the negative 2t. All right. So then we can use that. Now that we know that we could do that s plus 2 out, I see that this part right here is my sine k is 1 in this point, t. And then we also need to multiply it out, like to put that function on the back. I'm going to do e to the negative 2t sine t. Okay, so that's how we can use that to work around getting these weird functions, like these fractions like that. How do we go backwards, manipulating this idea of the translation theorem? Okay, we're going to apply this to a diff EQ, and then we actually have a translation theorem on the t-axis that we will also take a look at.